Dr. M.C. Sundaraja. He completed his undergraduate studies from Madurai Kamaraj University and went on to complete his masters in structural engineering from the same. He is a doctorate from Anna University and he's also done his postdoctoral fellowship at the Queensland University of Technology, Australia. He has more than 17 years of experience in the teaching profession and he has also published papers in 39 international journals, 7 national journals, 27 international conferences and 51 national conferences. He has so far published 124 papers in various journals. He went on to receive the Best Research Paper Award from IFERP, a unit of VVERT and NIRE on 4th April 2015. He has also received Outstanding Faculty Award from the Venus International Foundation Faculty Award, VIFFA, in the year 2015. Currently, Dr. M.C. Sundaraja is now working as an assistant professor in Tyagarajar College of Engineering, Madurai.
Welcome to UGC lecture series in bioarchitecture. Today we are having a look on design of structures 2. In the previous lectures, we have seen the analysis and design of a rectangular beam under working stress method. In this lecture, we are going to have a look on analysis of flanged beams. Flanged beams means T or L beams. As I have already explained you, the T or L beam means T beams are called as the intermediate beams of the hall and L beams are called as the edge beams. And how to analyze these flanged beams by means of or by using the working stress method. So, here for example, this is a hall which is having a column arrangement like this. These are all the column location of column which has been arranged for the design of slab system and slab system for the building. Now, how to provide the slab system for this case? Normally, we are connecting the columns by means of the beams and providing the slab over this beams. So, here this is the cross section of or longitudinal section of the slab which is supported over the beams. These beams are normally designed as or analyzed as T or L beams. So, here this intermediate beams are designed as T beams. So, here T beams means the beams with the flange portion is called as T beam, that is flange on either side of the web portion, and the L beam inverted L, it is called as inverted L beam, that is called as L beams. It's in the shape of inverted L. So, here in the case of L beam, it is having the flange on only one side, that is the edge beams are designed as L beam or analyzed as L beams. Only the difference between these two beams are it is in the shape of letter T, it is in the shape of inverted letter L, but in the case of T beam, it has flange on either side of the wave portion or either side of the rectangular portion. But here it is the flange which is having on only one side of the web portion, but the analysis and design of these two beams are almost the same. These two beams are generally called as flanged beams. So, these two analysis and design of these two beams are almost same, only the difference is the flange portion. In the case of T beam, the flange is provided on either side of the web portion, but in the L beam the flange is provided on only one side. So, now we are going to start analyzing the T section, that is flanged sections. Here also it is having 3 sections. One is balance section, under reinforced section, over reinforced sections. We have already discussed in detail about these 3 sections. Anyway, I am repeating. And normally the reinforced concrete designs, the reinforced concrete members are designed on the basic assumption that the stresses in the materials reaches their maximum permissible stresses at the same time. Both the materials are stressed to their maximum allowable stresses, one and at the same time, that section will be called as balanced section. In the case of under reinforced section, so the under reinforced section means normally we all know that from the under reinforced, it is less, it has less steel. So, if less steel than that required for the balance section is provided, that is under reinforced section. And in this section, the steel is stressed to its maximum permissible value first, while the concrete is stressed below the permissible value. Under such condition, this beam will fail initially due to overstress in steel. So, the type of failure which occurs in the case of this under reinforced section is tension failure or ductile failure. Now, we come to the over reinforced. Over reinforced automatically known as if the beam is over reinforced, it is if steel is provided more. If the steel is provided more than the required for the balance section, the section will be called as over reinforced section. In such condition, in this section, this concrete is stressed to its maximum permissible value first, while the steel is stressed below the maximum permissible value. Under such condition, this section will fail initially due to overstress in concrete. So, the type of failure which is normally occurred in the case of this section is brittle failure or sudden failure. So, these two sections are called as unbalanced section normally. So, in the case of unbalanced section, the neutral axis is going to be situated at the center of gravity of the section. In the case of under reinforced section, the failure of section is a tension failure. The steel is stressed to its maximum permissible value first. So, here we are using more amount of concrete. So, this neutral axis is going to be situated at the center of gravity of section. So, since it is, so the neutral axis moves upwards. So, here when compare x with x c, here x is less than x c. But in the case of balanced section, x is equal to x c, where x is the actual depth of neutral axis for unbalanced section, x is the depth of neutral axis for balanced section. But in the case of over reinforced section, here we are using more steel, so automatically concrete area will be less. So, it moves towards bottom. The neutral axis is going to be situated at the center of gravity of the section, it moves towards bottom. So, here x is greater than x c, that is the neutral axis portion of the unbalanced as well as the balanced section. Once you find out x c and then find out x, we have to compare x with x c. If x is less than x c, we need to conclude our section is the unbalanced section. If it is x is greater than x c, we need to conclude our section is over reinforced section. If it is if x is equal to x c, then we need to conclude that section is balanced sections. Then now to find out the moment of resistance of a singly reinforced TRL section. Normally, singly reinforced means the section which is provided with the reinforcement at the tension zone only is called as singly reinforced. This is a T beam. This is a flange portion or slab portion, and this portion is called as the projected portion is called as web portion. If the beam is reinforced with the reinforcement at the tension zone is called as singly reinforced beam, and the tension zone only is called as singly reinforced beam. Now, how to find out the moment of resistance of the T beam? So, here there are two cases. When the neutral axis lies inside the flange, here there is a neutral axis. When the neutral axis lies inside the flange, what will be the moment of resistance of the beam? That is, case 1, x is less than or equal to df. It means that neutral axis lies within the flange or just at the bottom of flange. It is x is less than or equal to df. When the neutral axis lies within the flange, what is the moment of resistance of the beam? And when the neutral axis lies outside the flange, what will be the moment of resistance of that is x is greater than df. Now, we are going to have a look on x is less than or equal to df. So, here there is a T beam and Bf is the width of the flange and df is the depth of the flange. Since it is singly reinforced section, the beam is reinforced with the reinforcement at the tension zone. So, here d is the effective depth of the beam and BW is the width of the web. So, here first here is the, now you take, for example, I am having this is the neutral axis for this one, for example. Now, this is a stress equivalent stress diagram for balanced section. In the case of balanced section, both the materials are stressed to their maximum permissible value one and at the same time. So, that stress at the topmost extreme fiber is taken as sigma CBC, and the stress at the bottommost extreme fiber is taken as sigma ST by m, that is at the level of compressive steel. So, here this is XC and this will be D minus XC. Since it is a balanced section, by using similar triangle property, we can find out what is XC. XC divided by sigma CBC, which is equal to D minus XC divided by sigma ST by m, where sigma ST by m is the stress in concrete surrounding tensile steel. So, this is we have already discussed in the previous rectangular section, how the section, how that area of steel is transferred into the equivalent area of concrete surrounding tensile steel. So, this is sigma ST by m is the stress in concrete surrounding tensile steel, and if it is AST, area of steel, m into AST we all know that equivalent area of concrete surrounding tensile. If it is multiplied by modular ratio, that is m into AST is the equivalent area of concrete surrounding tensile steel. Now, to find out X, now first case, neutral axis lies within the flange. This is stress diagram. So, here I am taking this as the X. So, this is X is less than or equal to dF, case 1. Case 1, X is less than or equal to dF. Now, to find out X, so here this is take this as the unbalanced section. Okay, this is unbalanced section. When the neutral axis lies within the flange, what will be the depth of neutral axis? Normally, in the case of unbalanced section, neutral axis is situated at the center of gravity of the sections. So, here to find out the actual depth of neutral axis, we need to equate moment of area on compression side to the moment of area on tension side. Moment of area, we all know that is moment of area is area into a distance of CG from neutral axis, distance of CG of area from the neutral axis. So, the moment of area on compression side, that is equal to equivalent or moment of equivalent concrete area on tension side. Since we have already transferred the area of steel into the equivalent concrete area surrounding tensile steel. So, we have to equate the moment of area on compression side to the moment of equivalent concrete area on tension side. So, the moment of area on compression side is area of the compression side, this is the area of the compression side, that is BF divided into X. Distance of CG of this compression side from the neutral axis is X by 2, which is equal to the moment of equivalent concrete area on tension side, here it is m into AST into the distance of CG of this tensile steel from the neutral axis is D minus X, that is D minus X. So, this is a way of finding the neutral axis for the first case. So, when X is less than or equal to dF, then neutral axis lies inside the flange. Find out the moment of resistance if X is less than one. First, when we find out X, we need to compare with the depth of flange. we need to finalize here if x is less than or equal to df, the neutral axis lies within the flange, and also we need to check x with the xc. If x is less than xc, it is under reinforced section, and if x is greater than xc, it is over reinforced sections. Now, what is the moment of resistance for under reinforced section? MR is equal to T into Z. In the case of under reinforced section, the steel is stress to its maximum permissible value. So, the failure of section here, it is tension failure or the ductile failure. So, what is T here? T is normally force AST into sigma ST, that is force is stress into area. Now, here this is the compressive force C, which is acting at x by 3 from the topmost extreme fiber, and T is the tensile force which is offered by the reinforcement, and the distance between these two force is called as the lever arm Z, that is d minus x by 3, d minus x by 3. And another formula, MR is equal to C into Z, where C is the force is stress into area. So, here area is BF into x, area is BF into x, and the stress is, since the stress diagram is a triangular one, if we take sigma CBC is the stress at the top, the average stress is sigma CBC by 2 into d minus x by 3. But what does it mean? So, this is the moment of resistance of the T section when the neutral axis lies within the flange. So, here this is the moment of resistance which is equivalent to the moment of resistance of the rectangular section. So, here we come to conclude that when the neutral axis lies within the flange, the T beam should be designed as a rectangular beam of size BF by D. So, when the neutral axis lies within the flange, so it means that the beam has to be designed as a rectangular beam, and the beam has to be designed as a T beam. If x is greater than xc, or if x is greater than df, the beam has to be designed as a T beam. For listen. Now, second case. So, here BF is the width of the flange, and DF is the depth of the flange, and BW is the width of web, and since it is a wrongly reinforced section, the reinforcement of the tension zone is AST, and this is the effective depth of the section. Now, here the neutral axis lies outside the flange. What does it mean? Now, here this is the equivalent stress diagram of balanced section. I am taking sigma CBC is the stress at the topmost extreme fiber, sigma ST by M is the stress in concrete surrounding surfaces. This is a balanced section, both the material stress to their maximum permissible value one and at the same time, and XC be the depth of neutral axis for the balanced section, that is the critical depth of neutral axis, d minus xc is the remaining depth. Now, first step to find xc. So, since it is a balanced section, I am using the similar triangle property. Xc divided by sigma CBC, for the depth of xc the stress is sigma CBC, at a depth of d minus xc the stress in the concrete surrounding tensile steel is sigma ST by M. So, this is the formula to find out xc, or it may be written as xc by d minus xc is equal to sigma CBC by sigma ST by M. Now, we need to find out actual depth of neutral axis for the section. So, here I am taking this as the a stress diagram, equivalent stress diagram for unbalanced section. This is for balanced section, this is for unbalanced section. I am taking x as the depth of neutral axis, and this will be the d minus x. So, here when the neutral axis lies outside the flange, the portion above the neutral axis are divided into two portions. So, here one is the flange portion, then another will be the remaining web portion. So, when the neutral axis lies outside the flange, the beam is in the shape of a T section. So, when x is greater than df, the beam should be designed as a T beam. It should be analyzed as a T beam. When the neutral axis lies within the flange, if x is less than or equal to df, the T beam has to be designed as a or analyzed as a rectangular beam. So, here to find out x, for finding out x, since it is an unbalanced section, the neutral axis is going to be situated at the center of gravity of the section. So, we need to find out depth of neutral axis by equating the moment of area on compression side to the moment of area on tension side. So, the moment of area on compression side to the moment of equivalent concrete area on tension side. So, what is the moment of area on compression side? So, here we are having two portions above the neutral axis. First portion, the flange portion, that is Bf into df. This is the area of the flange portion. I can divide the portion above the neutral axis, that is a compression portion, is two portion, one is the flange portion and remaining a web portion, and this is taken as x minus df. This one, the depth of neutral axis is taken as x and depth of flange is df, the remaining depth here it is x minus df. So, first one is the flange portion bf into df, and distance of CG of this flange portion from the neutral axis here it is. So, this is df by 2. Normally, the CG of this portion occurs at the center of the CG is at the center, that is df by 2. Well, what is the CG of this flange portion from the neutral axis? X minus df by 2, x minus df by 2. This is the moment of area of the flange portion plus the moment of area of the web portion here it is. The area of the web portion, this is Bf into x minus df, sorry Bw into x minus df. And the CG of this portion, which is normally occurred at the center of this portion, if this is x minus df by 2 and this will be again x minus df by 2. This portion is x minus df, depth of portion is x minus df, and the CG is it's at the center x minus df by 2, and the CG of this portion from the neutral axis is x minus df by 2, which is equal to, this is the moment of area of the flange portion, that is f, and this is the moment of area of the web portion, that is w. So, here it is totally it is the moment of area of the compression side, which is equal to moment of equivalent concrete area of the tension side is equivalent concrete area of the tensile steel m into AST, and the distance of CG of this tensile steel from the neutral axis is d minus x. So, this is the formula which is used to find out. But here what does IS code says that the moment of area of this web portion is too small when compared to the flange portion. So, the moment of area of the web portion is very small, moment of area of web portion is too small when compared to flange portion, hence it is neglected. So, this equation can be further rewritten as Bf df into x minus df by 2, which is equal to m into AST into d minus x. So, this is the formula which is used to find out the depth of neutral axis by equating moment of area on the web portion to the moment of area of the flange portion. Next one, now we need to find out what is the moment of resistance. So, again we are going to find out the moment of resistance of the section. So, here in this section, if x is greater than x e, the neutral axis lies within the flange, and also if x is less than x e, it is under reinforced section. And the moment of resistance of the section is T into Z, that is A S T into sigma S T. So, before that, so here the neutral we have considered only the flange portion, and sigma C B C is the actual sigma C B C at the topmost extreme fiber, and sigma C B C dash is the sigma C B C dash is the stress at the bottom of the flange. So, here we have the stress diagram, here it is the trapezoidal one, and I am considering C be the total compressive force offered by the compression zone, which is acting at the C G y bar from the topmost extreme fiber. So, here the stress diagram is a trapezoidal one. This is sigma C B C, this is sigma C B C dash. So, here and the corresponding tensile force is taken as T, and the distance between these two forces d minus y bar. So, we need to find out what is this one is taken as df. Now, we need to find out the moment of resistance m into A S T into d minus y bar, where y bar is sigma C B C plus 2 into sigma C B C dash divided by sigma C B C plus sigma C B C dash into df by 3. This is the moment of resistance of the beam, and here next one is if x is greater than x e, it is over reinforced section. That is M r is equal to C into Z. C is we have already found, C is normally the flange portion, that is area of flange portion is B f into d f, and B f into d f is the area, and the stress is sigma C B C is the topmost extreme fiber, at the bottom of flange is sigma C B C dash. The stress is sigma C B C plus sigma C B C dash by 2, that is the average stress, into the lever arm is d minus y bar. This is the equation we have derived. So, where y bar is sigma C B C plus 2 sigma C B C dash divided by sigma C B C plus sigma C B C dash into df by 3. So, this is the way of finding the moment of resistance of the flanged section when the neutral axis lies outside the flange. When the neutral axis lies outside the flange, the beam has to analyzed as the flange portion, flanged section. That is all about the moment of resistance of the flange portion. Let us summarize this lecture. In this lecture, we have seen the analysis of singly reinforced flanged beam, that is T or L beam, when the neutral axis lies within the flange and the neutral axis lies outside the flange. So, this x is less than or equal to df and x is greater than df. Then we have found the moment of resistance C into Z is Bf x sigma CBC by 2 into d minus x by 3, and another formula here Bf df into sigma CBC plus sigma CBC dash divided by 2 into d minus y bar. This formula is to find out the moment of resistance of the T beam or L beam when the neutral axis lies outside the flange. This is the formula which is used to find out the moment of resistance for the flanged section when the neutral axis lies inside the flange or just at the bottom of the flange. In this connection, the questions are: determine the expression for the depth of neutral axis for the singly reinforced flanged beam when the neutral axis lies within the flange, and also find the corresponding moment of resistance. Second one, here also to find out the expression for the depth of neutral axis for the singly reinforced flanged beam when the neutral axis lies outside the flange, and also find the corresponding moment of resistance. With regard to the references, we can refer the IS core IS 456-2000, that is a plain and reinforced concrete code of practice. Here also we can refer a book one which is written by S. N. Sinha, that is reinforced cement concrete. Let us come to the end of this lecture. Thank you.